Many professionals in the industry operate under the misconception that an AI agent is simply a highly tuned chat model. Standard chatbots are stateless, single-turn text generators. You provide a prompt, they predict the most likely sequence of following words, and they stop. Because of this design, they are entirely isolated. They cannot read your file system, they cannot browse the live internet, and they cannot observe the results of their own outputs outside the immediate chat window. An agent is different. It is a software system where the large language model, or LLM, acts as the decision-making brain inside a larger orchestration framework of executable tools. Real autonomy comes from engineering a pipeline that connects text prediction to actionable consequences in the real world. The core of this pipeline is a repeating control structure called the agent loop. This flowchart maps the REACT pattern, short for reasoning and acting. It begins with the plan step, where the model evaluates its current context. Next, the system moves to the act step. Here, the model selects a specific tool from its available arsenal and executes it. Then comes the observe phase. The system takes the raw output and appends it back into the model's memory. Finally, in the reflect step, the model decides if the original objective is complete. If not, the cycle routes right back to the beginning. In code, this entire sequence is driven by a standard while loop that runs continuously until the task is finished or a hard-coded limit is reached. By wrapping a text generator in this deterministic cycle, we create an engine capable of sustained, independent problem-solving. To build this loop locally, we need to assemble 4 distinct architectural pillars. Looking at this structural diagram, the first pillar is the large language model at the center. It functions strictly as the logic controller, reading inputs and routing decisions outward. The second pillar consists of the tools. These are the executable functions, like reading a database or writing a file, that the model can trigger. The third pillar is memory. This module stores the conversation history and the outputs of previous actions, feeding that ongoing context back into the central decision node. The final pillar is the orchestrator. This is the overarching Python script that encapsulates the other 3 components, actively moving data between the model, the memory, and the tools. The language model alone cannot act. It is simply one modular component within a larger software system. The main engineering challenge in building this orchestrator is translation, converting the model's unstructured text output into strict commands a computer can execute. This split view illustrates the industry-standard solution, native function calling. Here, the model generates a structured JSON payload. JSON, or JavaScript Object Notation, is a standard text format used to store and transport data, which maps perfectly to the required parameters of our local Python functions. Cloud platforms enforce this by requiring the model to format its response against a highly specific, predefined schema. However, this approach relies on models that have been explicitly trained to generate flawless JSON objects every time, which isn't always possible with smaller, local setups. When running smaller open-source models on consumer hardware, we need a more flexible method to extract commands. As we see in this diagram, we can prompt the model to wrap its commands in standard XML tags. We then use a regular expression, a sequence of characters that specifies a search pattern in text, to isolate and extract exactly what sits between those tags. Once the Python orchestrator extracts that specific string, it uses the built-in subprocess module to run the command directly in the operating system's terminal. After the system executes the command, it captures the result. If the code fails, the terminal generates a syntax error, and the orchestrator pipes that exact error text straight back into the model's context array. Because the model can now read the error it just caused, it can evaluate what went wrong, rewrite the code, and try again. By mastering these precise string parsing techniques, we create the critical bridge that lets a text generator manipulate a live operating system. Writing custom string parsing scripts works for basic local tasks, but it hits a wall when you need to interact with dozens of complex enterprise services. Manually hard-coding a new Python function for every database, API, and file system your agent needs to touch requires endless maintenance. To solve this, the industry is adopting the Model Context Protocol, or MCP. This network topology shows how MCP establishes a JSON RPC connection, a protocol for executing code on remote servers, to link a single client to multiple specialized servers. MCP removes the tool logic entirely from the agent's core script, pushing the execution workload outward to the connected services. The client dynamically asks the server for a list of available tools. When the model decides to act, it sends an execution request over the network. The remote server performs the actual database query or file change and simply returns the final result. This standardized protocol allows agents to scale securely, connecting to external services without requiring custom integration code for every new tool. Once an agent can reliably connect to external tools, we can expand the architecture to handle complex, multi-step engineering workflows. Instead of forcing one massive language model to manage every part of a project, developers are deploying multi-agent systems. A primary orchestrator node receives the objective and assigns subtasks to specialized worker nodes. Each worker executes its own React loop, passing verified outputs horizontally to one another, combining their work before sending the final result back up the chain. The most efficient way to build enterprise AI is to coordinate networks of small, highly focused agents rather than relying on a single, generalized model to do everything. But this level of automation introduces severe engineering risks. Granting an autonomous reasoning engine unchecked root-level access to your local terminal means it can accidentally overwrite critical system files or execute malicious code pulled from the web. To prevent this, developers must enforce strict local sandboxing. This usually means running the agent's execution loop inside an isolated Docker container, a standardized, secure environment that restricts access to the host machine and blocks unauthorized network traffic. Returning to our React loop, we also have to install hard programmatic guardrails. We add a max iteration limit to cap the total number of loops and a timeout clock to monitor any single action. If the agent gets stuck repeatedly trying to fix a broken script, the iteration limit cuts the cycle. If a command hangs indefinitely, the timeout forces the system to move on. Building an AI agent is an exercise in system constraints. It is the engineering of rigid boundaries, precise parsing, and secure environments that safely translate probabilistic AI reasoning into deterministic autonomous action.